Today we want to talk about similarity transformations, and if we have some time, maybe we'll start on how do we diagonalize symmetric and Hermitian matrices and what's the Schutz lemma. So let's start with the similarity transformations. Similarity transformations. So there exists a vector space. There exists a vector space V of dimension n, with basis beta, set of these n vectors, alpha 1 up to alpha n, be the unit orthonormal vectors. And this is the coordinate system. In simple words, this is the coordinate system for the vector space for all vectors V belonging to the vector space. M is non-singular matrix. M is a non-singular matrix that transforms the coordinate system of V from beta to beta prime, which is set of these mu n vectors, where alpha I prime is simply m times alpha I. Just think about it. If we have the three-dimensional coordinate system, you are probably familiar with I, J, and K, which are unit vectors. One along the x-axis, and the other along the y-axis, and third along the z-axis. But any 3x3 matrix with independent columns can be used to generate the three-dimensional space. So once these columns are independent, you can always orthogonalize due to using Gram-Schmidt, and then you can generate the entire three-dimensional space. So the number of vectors in the basis is fixed, but the basis is infinitely many. So this is the same thing, that you have some set of basis vectors alpha 1 to alpha n, which generate the vector space V. Now we have a singular, non-singular matrix M, and we generate another coordinate system, and from there we generate V again. Okay, so eigenvectors, no. So we operate on some vectors. So we want to tie the eigenvalues and eigenvectors to this transformation. So we want to operate on some vectors, in new coordinate system, with matrix A, which can be singular or non-singular. Doesn't make a difference, singular or non-singular. The only condition on non-singularity is on M, nothing else. So singular or non-singular, and the picture is something like this. So you have gamma in the old system. You do a transformation by M, you get M gamma. This is the vector in the new system. New system means new coordinate system. You operate on M gamma, in the new coordinate system, you have this matrix A. You operate on M gamma. So you get A times M times gamma. Now, since M is non-singular, I can go back. And now I have M inverse A M gamma in this order. And if I have B in the old system, so what is B equal to? But this should be equal to B gamma. So this implies B equals M inverse A M. Right? So the question is, what matrix? So the question is, what matrix would A correspond to? Would A correspond to in the old system? And the answer is B equals M inverse A times M. And we say, which implies A and B, which is equal to M inverse AM, are similar. And we say A and B are similar. So going from one to another is a similarity transformation. So this implies going from one to another. So going from one to another is a similarity transformation. Okay. And what are some of the properties? So normally we write this as, so we say A tilde B. So this is the notation for A similar to B. So this implies A is similar to B if and only if there exists an M which is non-singular and such that B equals M inverse AM. So this is the notation when you say A similar to B if and only if. So this double-headed arrow is the line with the double-headed arrow is if and only if there exists a non-singular M such that B is equal to M inverse M. So what are the properties of similarity? So we say this is reflexive. So reflexive means A is similar to A. So A is similar to A for n by n matrices. So A is similar to A for n by n matrices. Why? If M is equal to I, this implies M inverse AM equals I, A, or A, equals I, A, or which is equal to A. This similarity transformation is symmetric. Symmetric means if A is similar to B, then this implies B is similar to A. Works both ways. So if A is similar to B, this implies B is equal to M inverse AM. Or if I multiply M on this side, I'll get MB equals AM. Or I can multiply M inverse on this side. So this implies A equals MB M inverse. which is equal to Q inverse BQ, where Q equals M inverse. So this relationship implies B is similar to A. B is similar to A. This similarity relationship is also transitive. Transitive meaning if A is similar to B and B is similar to C, this implies A is similar to C. So A is similar to B implies there exists an M, which is M inverse AM, and B is similar to C implies C is equal to some R inverse BR or this is equal to R inverse M inverse A M R, which is equal to M R inverse, because when you take the inverse, the order reverse is over here, A times M R, which is equal to some T inverse A times T, where T is some M R, or this implies this thing. Sorry. This thing implies CA is similar to C or C is similar to A, because this is the relationship is symmetric. And similarity is an equivalence relation. Similarity is an equivalence relation. Equivalence relation R A comma B on the set of all n by n matrices over any field, over any field. And what is RAB? So equivalence, what is equivalence relation? So equivalence relation is a statement. Equivalence relation is a statement about every ordered pair A comma B from S by S, this is a Cartesian product, which is either true or false, which is either true or false. So it's a binary relation on a set. So equivalence relation is actually a binary relation on a set. So question is, what do similar matrices have in common? So question is, what do similar matrices have in common? And with a special choice, common, and with a special choice of M, with a special choice of M. We already know if M is a set of eigenvectors, then you have a diagonal form. So A is similar to the diagonal matrix. And with a special choice of M, what special form can be achieved by? And if we don't have a full set, then obviously we have the Jordan form. So either the matrix is similar to a diagonal form or it's similar to a Jordan form. So what special form can be achieved can be achieved by M inverse A M. So this is the question, and we can answer this question and the answer, the quick answer to this question is eigenvectors of A went into columns of S, went into columns of the matrix S, which made S inverse AS a diagonal, or maybe made S inverse AS diagonal, not a diagonal. Made S inverse AS diagonal. So S inverse AS, so A was similar to a diagonal matrix. For A equals A transpose, for the symmetric matrix case, we had Q instead of S, and for A Hermitian we had U instead of S. So we had Q transpose AQ equals the diagonal matrix in this case, and in this case we had U Hermitian AU equals to diagonal matrix. Both diagonal, these are both real, because eigenvalues of symmetric matrices and Hermitian symmetric matrices are the same. Are always real. Okay. So where do we use this transformation, the similarity transformation? So for that, so M inverse AM arises in differential or difference equation. In differential, or when we had powers of A, or we had E of AT, if you recall, or differential or difference equations. When U equals M times V. So if you recall, we had du over dt equals AU. This implies this becomes M dV by dt equals AMV, or dV by dt, since M inverse exists. So I multiply M inverse here, I multiply M inverse here. So I get this is equal to M inverse AMV, right? And similarly, for the difference case, U of n plus 1 equals A times U of n, or M into V of n plus 1 equals A times M times V of n. Again, multiply M inverse here, multiply M inverse here. This implies V of n plus 1 equals M inverse AM Vn. And in the special case, when M is equal to S, system is uncoupled because of the diagonal matrix. System is uncoupled because off diagonal elements are 0, because lambda equals S inverse A. S is diagonal. Okay. So I claim similar matrices have same eigenvalues. So how do we prove that? So similar matrices have same eigenvalues. So similar matrices have same eigenvalues. And how do I prove that? So I know B equals M inverse AM. Okay, so B minus lambda I equals M inverse AM minus lambda I. This I can write as M inverse M. So let me write this as M inverse AM minus lambda M inverse M. So M inverse, I take it out from this side, take it out from this side, M I take it out from this side. So this becomes M inverse A minus lambda I, A minus lambda I, and M on this side. So if I take this determinant, which is the characteristic polynomial, this would be determinant of M inverse, determinant of A minus lambda I, and determinant of M. So from chapter 4, you should know that the determinant of M inverse equals 1 over the determinant of N. So this is 1. So this combination is 1. So this is equal to the determinant of A minus lambda I. This is the characteristic polynomial of A. This is the characteristic polynomial of B. Their roots give the eigenvalues. So obviously, this implies eigenvalues of A and B of AB are same. Okay. What about the eigenvectors? So similar matrices have same eigenvalues. What about the eigenvectors? So suppose, what about, so question is, what about eigenvectors? What about eigenvectors? So B equals M inverse A times M. B is equal to M inverse A times M, and this implies A, B have same eigenvalues. A, B have same eigenvalues. We just proved this one, have same eigenvalues. And we'll show every eigenvector of A, every eigenvector X of A corresponds to an eigenvector M inverse X of B. So how do we show that? So we know AX equals lambda X, or this implies M inverse MB. It's not M inverse. So if I multiply M on this side, I multiply M on this side, then multiply M inverse on this side. So I multiply M inverse on this side. So this is MB M inverse into lambda into X. This is equal to A. Or this is equal to, if I lambda is a scalar, so remember this is a scalar, so I can move lambda anywhere. So we have, so this implies MB M inverse X. So this is A from here. So MB M inverse X equals I'm sorry, this is, I've already written over there, so don't need to do it here. So this implies MB M inverse X. MB M inverse X equals lambda times X. right? Because this is A. So if I multiply M inverse on this side, this means I multiply M inverse on this side, or B times M inverse X equals lambda times M inverse X. So this is an eigenvector, this is a vector, this is a vector scaled version here. So this implies M inverse X is an eigenvector of B, okay, with the same eigenvalue. Okay, so let's continue with our similarity relationships and see what other properties do they hold. So A is similar to B implies A transpose is similar to B transpose. And how do we do that? So we know B equals M inverse A M, or this implies B transpose. If I take the transpose of both sides, so this will be M inverse A M transpose, which is equal to M transpose A transpose and M inverse transpose. So I can always do M transpose. So let me write it first like that. So this is M inverse transpose, but I can always interchange these two. So this becomes M transpose A transpose M transpose whole inverse. So where so this is equal to, maybe where is later on, this is equal to Q inverse A transpose Q inverse A transpose, sorry, this is B, and Q here where Q equals to Q inverse equals to M transpose. This Q is not an orthogonal matrix, this is some other matrix. So maybe I put R over here. R. So R inverse MT. So R inverse is the transpose of M. So R inverse A transpose M. So this implies, so the same as M inverse A times M. So this simply means A transpose is similar to B transpose, or B transpose similar to A transpose. Okay. If A is non-singular, and A is similar to B, then this implies B implies, so this implies A inverse is similar to B inverse. And how do we do that? So A is similar to B implies B is equal to M inverse AM. This implies the determinant of B is the determinant of M inverse times the determinant of A times the determinant of M. This is the determinant of A because these two, the product is 1, we just showed, and this is not equal to 0. So B is also non-singular. So if B is non-singular, so this implies, so B implies B is non-singular. So I can always take the inverse. So if B is non-singular, let me take the inverse of this thing. So if I take the inverse, so implies B inverse exists. So if B inverse exists, so B inverse is simply M inverse AM whole inverse. So inverse, you reverse the order here. So this becomes M inverse, A inverse, inverse goes back to this same one. So this implies A inverse is similar to B inverse. Okay. Or in general, if A is similar to B, this implies AN is similar to BN for all n provided A inverse exists. So if this exists, then this would hold. Also, if A is non-singular, this implies A inverse times A times B times A should be equal to BA. right? Because this should be equal to identity and this should be equal to BA. And I can always, what I can do is matrices, this is associative. So I can always do like this. If I do like this, so this means, so this is an inverse matrix, this is BA, so this implies AB is similar to BA. So this is some matrix M inverse, this is M, this is the original family matrix A, and this is M inverse A, M, so this is equal to, so both these are similar matrices. Or, and also, if B is non-singular, this implies I can again write the same equation, B inverse BA, B inverse BAB. If I do that, so since this is identity, so I can always, so this is always going to be equal to AB. But again, since matrix multiplication is associative, if I put a parenthesis over here, this simply means BA is similar to AB. Although actually we could have also said it from here, because if this is symmetric to, since the similarity transformation is symmetric, so since AB is similar to BA, so BA should be similar to AB. Okay, so let's look at an example. So goal is always to find M such that M inverse AM is as close to a diagonal as possible. So A equals 1, 0, 0, 0. This implies my eigenvalues are on the main diagonal. Lambda 1 is equal to 1, lambda 2 equals 0, and B is equal to M inverse AM, which will have the same eigenvalues. So if M equals 1B 0 1, this implies M inverse is equal. So what is the determinant here? Determinant here is 1, main diagonal, off diagonal is 0. So M inverse is equal to, I swap these two, put a minus here, 0 here. Okay. And what is B? So this implies B, which is equal to M inverse AM equals to, so this is M inverse 1 minus B 0 1. And what is A times M? So A times M is, so I am picking the first row here because this is 1 0, so I pick the first row here. So AM is 1B, this is AM, and then there is no contribution of the others, so this is 0 0. And what is this equal to? This is simply equal to, so 0 1 means I am picking the last row, so 0 0 here, and this means I am weighing the first row by 1, and I'm weighing the second row by minus B. There is no contribution from the second row, so all I get is the first row, which is 1 and B. Okay, and what are the eigenvalues here? 1 and 0. So the eigenvalues, so lambda 1 is 1 and lambda 2 is 0. Same eigenvalues as this case, same. Okay. And what if M equals 1 minus 1, 1, 1? Again, the determinant of M is 1 minus minus plus plus, so this is 2. So this implies M inverse equals 1 over 2, and these two are swapped, minus 1 here, plus 1 here. Okay. And what is B times, what is B, which is M inverse AM? This is equal to, M inverse is, again, I put a half here, I put 1 minus 1, 1, 1 here. And what is AM? So AM, this means, sorry, again, so again, if I have 1 0, this means I'm picking the first row, so this is 1 1, so this is AM, and then because of the 0 0, there is no contribution, so this is 0 0, and this is equal to, again, so because of this one, first row is as is, minus 1 of, so the second row is 0, so there's no contribution, so we have only the first row here. So half here, and then 1 1 again. I simply add both of these, so there is no contribution here, so it's again still half. And this is a projection matrix, if you recall. If this is the projection matrix. And what are the eigenvalues? So the eigenvalues are half minus lambda square minus half square. So again, treat this as some a, treat this as b. So I have a square minus b square. So this implies half minus lambda minus half minus lambda plus half. So a minus b, a plus b, this is equal to 0, this is equal to 0. So maybe I say this is 2, this is 1. So this implies lambda 2 equals 0, and this implies lambda 1 equals 1. So again, the eigenvalues are 1 and 0, which is the same as the eigenvalues of the original matrix A. Right? Okay. And if M is some arbitrary A, B, C, D, M is some arbitrary A, B, C, D, this implies B is an arbitrary matrix. This implies B is an arbitrary matrix, with lambda 1 equals 1 and lambda 2 equals 0. M inverse AM has same number of eigenvectors, has same number of independent, has same number of independent eigenvectors as A, where each eigenvector is the multiple of M inverse. Okay. So let's move on and see what is a special form of a matrix when M is a unitary matrix. So triangular forms with a unitary M. So now specifically, M is a unitary matrix. M is a unitary matrix. So this is no ordinary M. So M transpose M is an identity. So we want to restrict M to be a unitary matrix. M to be a unitary matrix, which implies T equals M inverse AM, and this T is triangular. So we're going to move on from triangular to a diagonal matrix, but let's see. So we have the Schur's lemma. So lemma is when you're doing a bigger proof, then you have some statements of facts. So there is a unitary matrix. There is a unitary matrix M equals U, such that U inverse AU is triangular. Eigenvalues. So if you recall, for a triangular matrix, eigenvalues appear on the main diagonal. So eigenvalues appear along the diagonal. Of this fence. So this also means A is similar to T. So along the diagonal of this similar matrix. Okay, so where is the proof? How do we prove this one? So I'll give you a sketch of the proof. So the proof is, and then we are going to do an example. So just to show you if this works or not. So the proof is, let x1h into x1 be equal to 1. So bases for Cn are x1, u1 up to un minus 1. So these are n. So these are n vectors. First one is the eigenvector. And we say we form u1, which is an n by n minus 1 matrix. So u1 is formed like this. So u1 up to un minus 1. And let's form p1 equals, the first column is x1, and then I have u1. Okay, so it's a partition matrix. This is unitary. So P1 is unitary. So this is actually n by n. This is n by n. So first column here, n minus 1 column is there, and this is n. So this is unitary. Why? Because these are the bases. So obviously they are orthogonal. So P is unitary implies U1H, this one, and X1. This is 0 because X1 is orthogonal to all ui for all I because of the basis condition. Okay, so we say P1H A times P1. This is equal to what? So this is equal to X1H partitioned U1H into AP1. So what is AP1? So AP1 is going to be lambda 1 x1, and then we'll have A times U1, right? So this is P1. So when I have A over here, so A times x1 is lambda 1 x1. So this is an eigenvector actually. This is an eigenvector. This is an eigenvector of A. So A times x1 and A times u1 is like this. And what is this equal to? This is equal to, so when I multiply this row by this column, I have lambda 1, right? And then when I multiply this one by this one, I'll have x1h A times u1. This is a matrix, sorry. It's not a vector. u1. And this should be u1h term, this should be 0. This is 0. And u1h A u1. So this is u1h A times u1. Okay, so this is multiplied by this one. You get this because this is orthonormal. And then when you multiply this one with this one, this is x1 A u1. When you multiply this with this one, you get 0. Why? Because these are orthogonal. And then when you multiply this one with this one, you get this thing. Okay, so if A equals A Hermitian, this implies P1H A P1 is also Hermitian. Is also because if I take the Hermitian of this product, so this will be P1H into AH into P1, but A is equal to EAH, so this is also Hermitian. So this is also Hermitian. If this is also Hermitian, this implies X1H A U1 should be equal to 0. This should be equal to 0. So because this is a symmetric matrix, obviously both these should be equal to 0. Okay. So now U1H, this one, U1H into A into U1 is some A2, is equal to some A2 since P1H into A into P1 is similar to A, right? So this implies A2 has eigenvalues, has lambda 2, lambda 3, lambda n of A. because for similar matrices, the eigenvalues are the same. Okay. So then there exists an n by minus 1 times n minus 1 unitary matrix Q2 such that Q2H times A into Q2 equals lambda 2 x2 0 and A3. Okay, where A3, so using the same procedure as we did up in the above derivations, where A3 is n minus 2 by n minus 2 with eigenvalues lambda 3 up to lambda n, or we can generalize this thing, or Qi Hermitian A times Ai times Qi equals some lambda I xi 0 and A into I plus 1. Okay, so let's define. So if we define n by n unitary matrices pi equals I minus 1 0 0, and this is some Qi. So this implies PH A times P is some T which is upper triangular, which is equal to some upper triangular where P equals P1 up to Pn minus 1. These are all unitary matrices, and product is also a unitary matrix. So unitary matrices where first column of P, which we took as x1, first column of P is an eigenvector, and others in general are not. So this is just a sketch of the proof, which just tells you, okay, if you take M to be a unitary matrix, you will get a triangular form. So you get an upper triangular matrix. And let's look at an example before we end today's lecture. So let's say A equals 2 minus 1 1 0. This implies A minus lambda I equals 2 minus lambda into minus lambda plus 1, which is equal to lambda square minus 2 lambda plus 1, or this is equal to lambda minus 1 whole square equals 0, or lambda equals plus minus lambda 1 equals lambda 2 equals plus 1. And what are my eigenvectors? So what are the corresponding eigenvectors? So the corresponding eigenvectors are if lambda 1 equals 1, then I have, this implies A minus lambda 1 I equals 2 minus 1 is 1, minus 1 1 minus 1, or this implies minus R1 plus R2. If I do the row echelon form, this is minus 1, this is minus 1 plus 1 plus 1 minus 1 0 0. So what is the dimension here? So the dimension, or the nullity, so the dimension of null space of A minus lambda 1 I is equal to So, so the rank is 1 because this is one pivot. So the dimension is n, which is the number of columns, minus the rank, which is 2 minus 1, which is equal to 1. So this should be implies, this implies only one eigenvector, only one eigenvector in the null space, in the null space. There's only one eigenvector in the null space. Okay, so this implies x1 equals, so this is a free variable, goes on this side, comes plus 1, and I can always normalize it, and I can say this is plus 1 over under root 2. So this minus 1 goes over here, negative of this one, so this is 1 over under root 2. Okay, so if this is x1, I want a matrix U. So what is U? So U is, this is unitary or orthogonal in our case, because it's unitary or orthogonal. So I can always select a vector which is orthogonal to x1, and that should be, so 1 over under root 2, 1 over under root 2, and then I say 1 over under root 2 minus 1 over under root 2. So if this is my eigenvector, this is my eigenvector, this is some other u1. Okay, and both x1 and u1, so you can check x1 dot u1 equals 0. So they are orthogonal to each other. So what is u inverse a times u? So u inverse, so what is the determinant here? So determinant of this one is half, minus half, this is minus 1. If this is minus 1, so this should be minus 1. So minus 1, and when I do the inverse, so let me do the inverse first. So when I do the inverse, these switch. So minus 1 over under root 2 here, plus 1 over under root 2 here, and then I have minus 1 over under root 2 here, minus 1 over under root 2 here. But since this is minus 1, I do plus, plus, minus, plus. Okay, and then I have a is 2 minus 1, 1, 0, 2 minus 1, 1, 0, and my u is again, so this is a symmetric matrix, so obviously this is the transpose only, and the transpose only is this one, and this is symmetric also. Maybe I write here symmetric. So this implies, and this, since it's unitary, so u equals I, or this implies u inverse is simply u h, or which is equal to u transpose in this case, which is the case over here. Okay, and u is 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root 2. And if I multiply this out, so if I multiply this out first, this is equal to, so I have, because of this 1, 0, I am only taking the first row. So this is 1 over root 2, 1 over root 2. There is no contribution of the second row. From here, I have 2 over under root 2 minus 1 over under root 2. 2 over under root 2. So the first row is multiplied by 2. The second row is actually multiplied by minus 1. So 2 minus 1, so it's 1 over under root 2. And then I have 2 under root 2 plus 1, so this is 3 over under root 2, and when this is multiplied by this one, so this is equal to this one, and or u inverse au equals, so when this is multiplied by this one, this whole thing, so again the first row is multiplied by 1 over root 2, and the second row is also multiplied by 1 over 2, and then you add them up. So half plus half, this is 1. Half plus half, this is 1. This is 3 halves plus half, 3 halves plus half, 3 over 2 plus 1 over 2 is 4 over 2, which is 2. This is, you subtract, so same here, so it's 0. 3 by 2 minus 1 over 2, which is 2 by 2, which is equal to 1. And this is some triangular matrix. So this is an upper triangular matrix. So if we have, so we just showed if we pick, if we pick, if we have a matrix which only has one eigenvector, so this is the only eigenvector, only one corresponding to eigenvalues, to two eigenvalues, and if I pick the eigenvector, the first column, if I pick the first column as the eigenvector, and I pick any orthonormal vector as a second column, which is orthonormal to the first to the eigenvector, and if I do the similarity transformation, then I get an upper triangular matrix. So this is just to show, if you have a unitary matrix, then M inverse AM, then M inverse AM is kind of is a triangular matrix if M is unitary. So this is what we showed, and this is what we want to do. Okay, if we pick U, or what matrices A would make this triangular into a diagonal matrix, and what if we cannot, then what is the form that is possible. So that is the next two lectures. Probably half of the lecture of half of the next lecture is going to be on Jordan form, and then there's a complete lecture, the last lecture of this chapter, on Jordan form, or how to compute the Jordan form of a matrix which does not possess a full set of eigenvectors. Again, if you have any questions, you can uh, email me, or we can discuss it more during our discussion sessions on Mondays and Wednesdays. Thank you.